All right, so today we're going to talk about derivative rules. And one of the things we talked about before is that if you have a function f of x, then its derivative, f prime of x, can be calculated using what I like to call the limit definition of the derivative. And that's that f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Now we can calculate derivatives like this, but it takes a really long time. And so we have some rules that make it easier to calculate derivatives so we don't have to do that all the time. So one of the first rules is the derivative of a constant. If f of x equals c, well first, what does f of x equals c really mean? Well, f of x equals c means that the function is a constant, like the equation y equals 3. So if f of x equals c, then what's the derivative? Well, the derivative of a constant function would mean the slope of a horizontal line, and the slope of a horizontal line is 0. So if f of x equals any number, then f prime of x equals 0. So let's say y equals 4. Well, if y equals 4, then dy dx, just another notation for derivatives, is 0. 4 is a constant, 0. G of x equals e squared. Well, e is a letter, but no, it really stands for a number. It's 2.718, and so on and so on. So if g of x equals e squared, g prime of x is also equal to 0. Then when we come down here and we do the power rule, if f of x is x to a power n, and this works for any power of n, it can be positive, it can be negative, it can be fractions, it can be 0, any number n, if f of x equals that number, then f prime of x is n times x to the n minus 1 power. This means you bring the power down and reduce the power by 1. Now, when you go to take derivatives, you can take the derivative of a sum and a difference. And technically the rule's down here. And it says if y equals f of x plus or minus g of x. In other words, if y is the sum of a bunch of things or the difference of a bunch of things, then the derivative is just the sum or difference of the derivative of each part individually. In other words, when I come up here to take this derivative, dy dx is going to be the derivative of 4x squared plus the derivative of 7x minus the derivative of minus the derivative of 5. So derivative of 4x squared, I'm going to bring down the 2. So when I bring it down, I'm multiplying it. So 4 times 2 is 8, x to the first, 7x to the first. Bring down the 1, reduce that to a 0. Well, x to the 0 is 1, so the derivative of 7x is just 7. And then minus the derivative of 5 would be like minus 0. So 4x squared plus 7x minus 5 is 8x plus 7. Number 2, I really want this to look like a exponent rather than an exponent and a radical. So x cubed square rooted is the same as x to the 3 halves. And therefore our derivative is going to be 3 halves x to the, well, 3 halves minus 1 is 1 half. Same thing over here. I don't really like that this is a fraction. I want to undo that. So 5 over x to the 4th is the same as 5x to the negative 4. Then I'll take the derivative. H prime of x is negative 20, x to the negative 5th. Be careful. Bring down the negative, keep that. Negative 4 minus 1 is negative 5. So make sure you pay attention to your negatives. The constant multiple rule. If y equals c times f of x, then dy dx is going to be c times f prime of x. In other words, you ignore the coefficient, find the derivative using your rules, and then multiply that derivative by the original constant. So I usually tell people ignore the c, take the derivative, put the c back. That's about it. The sum and difference rule we went over. If you have a sum or a difference, you just take the derivative piece by piece. So if we come down here and do one more of these, y equals all this nonsense. Well, before I go to take the derivative, I'm going to make all these nice, simple exponents. So x to the 2/3 is fine. 4x over 9, no, I'd rather write that as 4/9 x, because now I have a coefficient and an x. Cube root of 7x is going to be 7x to the 1/3. Well, wait a minute. We haven't talked about when you have a 7 raised to 1/3. So you know what? I'm not going to leave it like that. 7x to the 1/3 is the same as 7 to the 1/3, x to the 1/3. and now I have a coefficient and an x, and then I have 10x to the 9th. And so our derivative dy dx is going to be, let's see, 2/3 x to the negative 1/3. Bring down the power, reduce it by 1. 4/9 x becomes 4/9. This guy right here, 7 to the 1/3, I'm just going to leave as the cube root of 7. It's a coefficient. And then the derivative of x to the 1/3 is 1/3 x to the negative 2/3. And then 10x to the 9th, 90x to the 8th. Do you have to change this? Nope. Leave it like that. Walk away. I don't care. Negative exponents? Fine. Fractional exponents? Fine. Don't touch it. Just leave it like that and walk away. Moving on to the back. We talk about the product rule. Now, we said if you're adding or subtracting, you can just take the derivative piece by piece and then put them back together. If you are multiplying or dividing, you cannot do that. You take the derivative using a rule. Adding and subtracting, piece by piece, is fine. Multiplying and dividing have their own rule. So the product rule is this. If y is f times g, then dy dx is f times g prime plus g, if I could actually write that, there we go, g times f prime. I usually say that as it's the first times the derivative of the second plus the second times the derivative of the first. I've also seen it written this way. D dx of u times v is u dv dx plus v du dx. The first times the derivative of the second plus the second times the derivative of the first, or using prime notation, it looks like that. There's also a song that goes with it. The product rule is so much fun. It's 1 prime 2 plus 2 prime 1. Oh, calculus, how tough are both your branches. All right, that's enough singing for a moment. So, practice with the product rule. Now, this one we can do using the product rule or using another method where we distribute and then use the power rule. So, I'm going to talk about both. So option 1 right here is if I use the product rule, I'm first going to think about these as x to the 1/2 and 2/9 x to the negative 1 plus 4x. Again, I want a coefficient and an exponent whenever possible. So then when I go to take the derivative here, y prime is going to be the first times the derivative of the second, and the second being everything in the parentheses. So that's going to be negative 2/9 x to the negative 2 plus 4. So there's the first times the derivative of the second plus the second times the derivative of the first. And I don't care if you distribute. You can write this down and walk away. Completely up to you. Now, the second option for something like this, and honestly is probably the way I'd go, is I'd distribute first and then use the power rule. So I want you right now to distribute first, then use the power rule. Pause, and then go. Pause. Welcome back. Look, it magically appeared. So if we distribute and then add the exponents, we get y equals 2/9 x to the negative 1/2 plus 4x to the 3/2. Using the power rule, we end up with that. So make sure that you understand that part. And then I want you to try example 2 on your own, and I would definitely use the product rule. Don't FOIL it out. If you want to, you can, but I probably wouldn't. So use the product rule, pause, and come right back. Welcome back. So look, magic. First times the derivative of the second. Make sure when you bring down that 1/3, 1/3 minus 1 is negative 2/3. And then negative 2 brought down becomes a negative 3. And then the second times the derivative of the first is right here. Now under the quotient rule. The quotient rule says if y equals f of x over g of x, then dy dx equals g of x times f prime of x. It's the bottom times the derivative of the top minus the top, f of x, times the derivative of the bottom, g prime of x, all over the bottom, g of x, squared. And now I'm going to sing. So there are songs to go with this. Songs, yes, plural. There are 2 songs. So if you have a quotient, f over g, then the derivative is the bottom times the derivative of the top minus the top times the derivative of the bottom For the rest, you won't be scared. It's all over the bottom square. This is calc, this is calc, this is calc. That was fantastic, wasn't it? It's the bottom times the derivative of the top minus the top times the derivative of the bottom. For the rest, you won't be scared. It's all over the bottom square. This is calc, this is calc, this is calc. And since that takes a long time to do and you have to pause to clap in the middle, which, you know, is fun, but if you don't want to pause to clap in the middle, I made up another one also. It goes to Mary Had a Little Lamb. Low D high minus high D low all over low times low. Low D high minus high D low all over low times low. So it's not as fun, but it's a little bit faster to sing. So yeah, that's our fun sung quotient rule. Low bottom times the derivative of the top, low D high, minus high D low, all over low times low. So the quotient rule, I will quickly go through one, and then you can do the other. So if I do the quotient rule down here, y prime is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Now this is just begging to be simplified because it's easy, so I am going to simplify this one. So I've got 3x minus 3x, so those are gone. 6 minus negative 7, so 13 on top, over x plus 2 squared. So there's our derivative there. I want you to pause, try example 2, and then come right back. Magic! Welcome back. Up here, should end up with this. Bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. This is not really begging to be simplified, so if you want to, go ahead. My rule for simplifying is this: when you're doing work out of the book, make sure that yours matches the back. So if that means you have to simplify, go for it. If that means you can look at yours and know that they're the same, fine, don't simplify. And when it comes to a test, you only need to simplify if it's a multiple choice, because if you get this and this isn't an answer, simplify it down until you can match it up with one of the choices. Okay? So now, down here, we are given all this information, and they want us to find f prime of 2. Okay, so here's g, g prime, h, and h prime of 2. Here's some f's. They want us to find f prime of 2. So let me show you how this works. What we're really looking at here is how do you deal with the notation? Well, if f of x is 2g of x plus h of x, then f prime of x says that if you're taking a derivative of a number times a function, the derivative is just the number times the derivative of that function. And then it also says if you're taking the derivative of the sum, you just take the derivative piece by piece and add them back together. So f prime of x is 2 times g prime of x plus h prime of x. They want f prime of 2, so f prime of 2 is going to be 2 times g prime of 2 plus h prime of 2. And if I look up here, they give me those values. 2 times g prime of 2 plus h prime of 2, which is 4, is going to be 0. Okay? So I want you to use the sum and difference rule, the product rule, the quotient rule. I want you to try these on your own, then come back and check up with what you did. Where'd my pause go? Welcome back. Okay, so 4 minus h of x. Your derivative is going to just be negative h prime. So you take the negative of h prime, which gets you negative 4. Come down to the next one, product rule. G times h prime plus h times g prime. Look at these values, substitute appropriately. Should get 14. And then last but not least, quotient rule, bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom square. Plug everything in, get negative 10. All right, and then on the last page, we're just going to do some examples with using tangent lines with these rules. So if we had something like this, find the equation of the line normal, remember that means perpendicular, to f of x at this, at the point where x equals 1, what we want to do here is say, well, the normal line is perpendicular to the tangent line, and the tangent line has a slope equal to the value of the derivative. So we need the derivative. And before I go to do that, I don't really like that this is a quotient. I prefer not to do the quotient rule if I can avoid it. So I'm going to rewrite f of x before I do anything else and rewrite it as x plus 5 minus 2x to the negative 1. Divide this by x, divide that by x, divide that by x, write it differently. This is way easier to differentiate than that. So if I want the equation of the line, I got to use the derivative. So f prime of x is going to be 1 plus 2x to the negative 2. I want the derivative at 1. So I want f prime of 1, which is going to be 1 plus 2 over 1 squared, which is 3. This is the slope of the tangent line. So that means that negative 1/3 is the slope for the normal line. I used m for slope. So this is going to be our slope for the normal line. And then I need a slope, I need a point. So I have x equals 1. Now I need a y value. To get the y value, I'm going to plug this back into here. So y, when x is 1, is going to be 1 plus 1, 1 plus 5, minus 2 over 1, which is 4. There's an x value, a y value, a slope. Y minus y1 equals m x minus x1. Okay? All right, find the equation of horizontal tangents. What's horizontal? Horizontal. Oh yeah, horizontal are those lines that go back and forth left to right, right? And what's unique about them is their slope is 0. So if I know I got to get a slope of 0, I need the derivative to be 0. So I'm going to take the derivative, set it equal to 0, and go from there. I want you to give this one a shot on your own and then come back. All right, welcome back. So I'm going to actually shade this so I can look at only a little bit at a time. Whoops. So I can look at just a little bit at a time. What we want to talk about here is this horizontal tangent idea. So I want to know when the slope is 0. So the first thing I did is I took the derivative, which is right about here, and I set it equal to 0. So here's the derivative. Here it is set equal to 0, factored, solve for x. So when x equals 7 and x equals negative 1, this graph has horizontal tangents. So if we think about x cubed and just think about the graphs of x cubed, they look something like this. So they have two horizontal tangents, at one x value over here and at one x value over there. So this is like my negative 1 and that's like my 7. Well, if I want the equation of the horizontal tangent, the equation of a horizontal line is a y equals. So I need to know what y equals when x is 7 and what y equals when x is negative 1. So that's what I did next. So if I come back over here and go to the right, I plugged in 7 for x and got y equals negative 242. That's the equation of the line because horizontal lines are y equals. Y equals a number. And then same thing for negative 1. Plugged in negative 1, got 14. So those are my two horizontal tangents. One more example, and then I want to talk about the table, and we're done. If something's written piecewise, you can take the derivative piecewise, but the difference is, in a piecewise function, you're not sure if at this break point, if the derivative is going to exist, because if your piecewise function looks like this, the derivative there can't exist because there's a jump. If your piecewise looks like this, the derivative here can't exist because there's a corner. But every once in a while you get lucky and you get a piecewise that comes down and then continues with the same slope, and at that point your derivative might exist. So that's what we're going to talk about right here. So if I have this function, the piecewise definition of f prime is just going to be the derivative piece by piece. It's going to be negative 2x, 2 goes to 0, and then negative 2 for x is less than 1 and for x is greater than or equal to 1. Nope, whoa, I said the wrong thing. Less than 1, greater than 1. Wow, that was a bad mistake. So when you break up your piecewise definition, it's just less than and greater than. You do not put an underline on anything yet. Then you need to check whether both of these conditions are true. If f of 1 if f of 1 equals the limit as x approaches 1 for f, then that means f is continuous, you're good to go. So if we want to test this, That's where I just come up here and plug 1 into both of these equations and see if they line up. So if I plug 1 into here, I'm going to get -1 plus 2, which is 1. And if I plug 1 into here, I'm going to get -2 plus 5, which is 3. Well, that means my limit from the left does not equal my limit from the right, so it's not continuous at 1. Therefore, the derivative can't exist at 1. Therefore, this is my derivative. Okay? So does the limit as x approaches 1 of f prime exist? This is a different question. As x approaches 1 for f prime, this goes to -2, that goes to -2. Yes, the limit for the derivative exists, but the derivative itself, f prime of 1, does not exist. Okay? It's a little quirky. We'll see things like that later. I've hit the 20-minute mark. All I want to talk about here is looking at derivatives. If you want to take a first derivative, that's y prime, f prime, dy dx, or this. If you want to take the second derivative, that just means you take the derivative of the first derivative. It looks like that. Once we get to 4 derivatives, that starts being a little overwhelming in the primes. We just start putting parentheses. Y parentheses 4 means the 4th derivative. F parenthesis 4, 4th derivative. Over here, though, we just keep using the numbers. Okay, I'm almost at 21. I hope you enjoyed yourself and enjoyed my singing. Have a good evening.